Okay, so we have seen this relation between the 1D Fourier transform of a projection to a 2D Fourier transform along theta equal to 0, that was fairly simple to establish. So today we will work out the more general case of theta not equal to 0. So we are talking about the inverse Radon transform, and how we can do this. Remember we wrote p theta of t was integral ds going from here to here, and I also mentioned that there are two different coordinate systems. For clarity I will probably draw them in different colors today. So this is x and this was y, and this was t and this was s, right. So the integral inside the Radon transform is integrated over s. So the Radon transform itself is not a function of s, it is a function of theta and t, and of course the angle that we had over here was theta, right, and so and t was in the normal direction, right, n hat dot r bar was equal to t, that was our equation of the line, and we discussed that you can transform from x comma y to t comma s using a rotation matrix, right. So Ts was just this cos theta sin theta thing, times xy. So t was again x cos theta plus y sin theta. We know this because this was our equation of our line, of a single line depending on the distance from the origin, in that n bar dot r bar is equal to t whatever, and so s of course is minus x sin theta plus y cos theta. So if you have not already seen this, or if you have not figured it out already based on our discussion in the previous session, this is what we will use to relate s theta of t, s theta of w rather, which is the Fourier transform. So this is Fourier transform of p theta of t with respect to the t variable for a fixed theta, right. We will relate this to f of uv, which is the Fourier transform of f, small f, right, which is the function we want to determine. So we want to get small f, we have measured p theta, so we can take a Fourier transform of p theta and we can relate that to the Fourier transform of f. So we can invert the Fourier transform of f and then get f, right. So that is a slightly long winded approach, but it is basically what we will do, okay. And right now this might seem a little bit mathematical, but once I show you what these things look like, it will be a little bit clearer, and hopefully you will be able to appreciate some of these transformations. Alright, so let us take a look at what this s theta of w is. Remember this was integral minus infinity plus infinity p theta of t exponential minus 2 pi I w t dt. This was the 1D Fourier transform of p theta of t, and if you write down the expression for p theta of t, you will get f of xy going along ds, that is what p theta was, right, times exponential minus 2 pi I w t dt, okay. So if you look at this, this is a two dimensional integral now, the double integral in t and s, right, and you can convert, of course x and y have to be written in terms of t and s as well, right, using this inversion of this guy which is with minus theta, but you can convert this entire thing to x and y, right. So remember we said that the Jacobian of this guy was 1 because determinant of the transformation matrix is 1. So ds dt is the same as dx dy. So we can convert this because because t and s are being integrated over, you can convert them into x and y and that will be integrated over, right, does not matter. So now you will just get, if you convert it back to xy, you will basically get f of xy, that will remain unchanged. You will get exponential of minus 2 pi I w times x cos theta plus y sin theta times dx dy, okay, that is s theta of w. So, let me just rewrite that. So, s theta of w was a double integral minus infinity plus infinity f of x comma y. If you go back, we had this exponential 2 pi I w times x cos theta plus y sin theta for t times dx times dy. Okay. Now, if you look at the guy inside the exponential, this is the same as w cos theta x plus w sin theta y. I have not really done anything, I have just reordered the two values. So, this is the same as some w bar dot r bar, where w bar is w cos theta comma w sin theta, right. We are only rewriting what we already have. If you go back and recall the 2D to Fourier transform expression, this had a double integral f of x y exponential of 2 pi I with a minus sign u bar dot r bar dx dy, and this u bar now was u comma v, right. So, the actual 2D Fourier transform had u comma v corresponding to u bar, and the s theta of w, the 1D Fourier transform of the projection, has w cos theta comma w sin theta, right. So, this basically means that s theta of w is nothing but f of w cos theta w sin theta. Okay, so, this is called the Fourier slice theorem. So, let us step back a little bit and think about what this means, right. This is purely algebra. To this up until this point, we have only done algebra, we have not really discussed what it geometrically means. You have a projection p theta, right. So, you have a projection p theta of t. You take its 1D Fourier transform and you get a value s theta of w. Okay. This projection, remember, is taken at an angle. So, you have your object, whatever, this is your xy direction, and then you have a projection taken at some angle. Okay. And of course, the angle is with respect to the normal, but okay, whatever, does not matter, right, or it can go above and come back. We will ignore that for now, this is just theta, right, parameterizing the p and this is your t. So, you take this signal, whatever you get here, the projection signal, which is p theta of t for this value of theta, you take a Fourier transform of it, right, which is what we have done here. And you will get s theta of w if you do a Fourier transform. And from the Fourier slice theorem, it basically tells you that if you go back in the frequency domain of u v, it gives you the value of the 2D Fourier transform along a ray, not only along any ray, but along a ray at an angle theta. Okay. Because remember, this is like f of u comma v, and if you convert this to polar coordinates, u comma v to w comma theta, then u is equal to w cos theta, v is equal to w sin theta. So, this chap s theta of w, if you take this function, so this will be some value, right, this is w and this is s theta of w. This function is basically giving you the value of the 2D Fourier transform along this ray. Okay, so, this is your w direction, w is like r, remember, keep this polar coordinate transformation in mind, right. So, you get one slice of the 2D Fourier transform from a single projection. Now, if you rotate it at another angle, you will get another slice. Let us say you rotate this detector by a little bit more. So, now it is all like this. So, you will get a different p theta of t corresponding to this theta now, right, corresponding to this normal and this now this angle, let us say theta 2, and you will get a corresponding p, and you take a Fourier transform and you get a corresponding slice. So now you know the value of the 2D Fourier transform along this line. Okay. Then you rotate it a little bit more, take another projection, you take p theta for that particular theta, take a Fourier transform, get s theta for that particular theta, and you will get another slice in the Fourier space. So in principle, if you were to measure the values of the projections for not 360 degrees but just 180 degrees, because you get front and back, remember. If you can measure the value of p theta of t for all of these directions, theta going from 0 to pi, then you will basically get all the information of the 2D Fourier transform along all of these rays. So now you will have the value of the 2D Fourier transform of the function f of u v, and you inverse transform that to get f of x y. Okay, and that is really all there is to it. So whether you have a parallel beam, you have a cone beam, you have a fan beam, you have equispaced detector, equiangular detector, it does not matter. All of that is just a manipulation to bring it to this form. There are some geometric maps you can do to bring it to this form, and once you come to this form, the Fourier slice theorem tells you how to invert it. Okay. So we will look at some examples just so that some of this abstract stuff becomes a little bit clearer. Let us look at a few examples and see how this is actually applied. I have a couple of images that are taken from Wikipedia, you can find them under Radon transform, but this is a typical sample data set that you can generate by yourself. So what we have here on the left is our actual function. So our function is non-zero here inside the white squares and it is 0 everywhere else. Okay, so this is our cross section. So assume this is a highly cartoonized version of somebody's head and you are doing a cross sectional scan. So you are passing X-rays like this, and you have a detector here and you measure, right, and you will get an intensity distribution. So if you get a large absorption, you will get a large value, something that looks close to white. If you get 0 absorption, you will get nothing, right, you will get a black signal, because we have taken minus log whatever IF by I naught, right, and so log 1 is equal to 0, so that automatically removes, it is like a dark field image basically. So the image you see on the right is something called a sinogram. Okay, it has nothing to do with China, it is just that if you take a single spot here, you will get a sine wave in this image as you rotate it, right, but that we will talk about that in a minute. So how do you interpret this? So this is your t axis and this is your theta axis. So if I start at theta equal to 0, that means I have my detector lined exactly parallel like this and my rays are going exactly like this. Then I will measure some p theta of t here depending on how much light is getting absorbed as the stuff goes through, right, and that will give me the first row of this image. Okay. And if you look closely, you will see that you have this distinction here, this is probably the first cube and this is the second the first square and this is the second square, right, and their edges are almost aligned, so you see they are almost next to each other. So then you rotate by a small degree, maybe 1 degree or 2 degrees, and then you do another scan. Now you will have to pass light at 1 degree like this, and then you do the same thing, measure the intensity, and you will get another one, the next row in this image. So you stack up the rows as a function of theta, always having t along the horizontal direction. This is what constitutes a sinogram. Okay. And this, like I said, so this is your f of x y representation and this is your p theta of t representation. This is also 2D representation, this is also 2D representation, both are absolutely equivalent. So if you did not know the left and you only knew the right, you can reconstruct it using the Fourier slice theorem to get the left, and if you only knew the left, you can generate the right by just evaluating these line integrals. Okay. So that is basically telling you what the right. So the right side image is the radon transform of the left side image. Okay. And you can play with this, you can create different types of cross sections on the left image, you will get a corresponding sinogram in the right image. Okay. Okay, here is another more animated example. So this the detector and the whatever is not moving, but the object itself is rotated equivalently, both equivalent, and you see how the sinogram is generated, right. So this is continuously being animated. So for example, if the detector is always kept, okay, detector is always here and the source is always here, okay. When the source and the detector are aligned, for example you look at the green fellow, when the source and the detector are aligned with the green object, that means its largest amount of absorption is happening, so you get a very bright image for the green object. These three are colored differently just to show you where they are coming from. Typically these are just intensity values, so there will only be grayscale images, right, and the left one will also be grayscale image, but this is just color coded to show you which is contributing to which sinogram, right. So the moment you have an alignment with this central rod like structure, you have a large intensity. If you look, when it becomes horizontal, this intensity will go up and then it goes down again, because the path length is reduced and the absorption is reduced, okay. So this is again typically how a sinogram is generated. If you take this axis now is your theta and this axis is your t, and it is only being animated to show you how these are generated. So at each particular instant is one row corresponding to the vertical section here, and you can use that and stack them up, and if you freeze this animation fully you will get a full sinogram, okay. And notice again also the information you have for theta equal to 0 is equivalent to the information you have for theta equal to pi. So you do not need a rotation by 2 pi, you only need a rotation by pi, because for theta equal to 0 the let us say the red square, I am not sure if I can get a blue square, but let us try this, yeah, and the blue square are like this. So the light coming from here is going to look at both, but for theta equal to pi the blue square is here and the red square is here, and the light coming here is again going to see the same thing, right. It does not matter which order they are seen in, because it is being integrated over, right, as the light goes from left to right. So you only need theta equal to from 0 to pi and not from 0 to 2 pi, okay. I hope that is clear from this illustration, okay. So typically the radon transform is t from minus infinity to plus infinity and theta from 0 to pi. Alright, so now I have here a full summary of the radon transform, and so you have initially some cross section which you do not know about, so you do not know what this looks like, but you only have the sinogram, let us say, right, for a 2D case. If you do that, then the first step is to take a single row in the sinogram and calculate its Fourier transform, okay. So you have, in this case it should be a column because this is the theta direction. So you take, remember the Fourier transform is in the t direction, right, this is t, and so you have to take a 1D Fourier transform, and then you take that particular value of the Fourier transform, the s theta. So this is your p theta of t, you calculate the Fourier transform, you will get an s theta of w. So in this case again it is actually the row, yeah. So you get theta equal to 0, you take a Fourier transform of that, you will get one value of s, this is the w direction. Now you take this fellow and you stack it along the radial direction in the 2D frequency space. So this now is your u comma v, and you have this single stack. So this, for example, this stack gets put here and this stack gets put from here over here and so on, depending on the angle. So depending on what the value of the angle is what the y coordinate is, or the vertical coordinate is, should not say y, the vertical coordinate is on the sinogram. Depending on this value, you orient this at a suitable angle in the UV plane. If you do that for the entire sequence of angles from 0 to 180 degrees, then you will get all the rays, right, for various angles 0 to, again this also should make it clear that you only need pi, because for 0 you have this side and this side being radial in both directions, and likewise for any other angle you have opposite quadrants, the ray goes through opposite quadrants. So if you do from 0 to pi, you will get this full 2D Fourier transform. Once you have the 2D Fourier transform, you invert it, take an inverse transform to get f of x y. Okay, and that will give you your actual image. So if you have a simple 2-dimensional situation like this, you have a sinogram, whatever, you can use this to reconstruct the f of x y. Okay, using this inverse Radon transform and the Fourier slice theorem. So that should be fairly clear now. So there are a few different configurations in which you actually get the data. We will look at that a little bit now, and then we will discuss that in more detail subsequently. But let us say you have a 3-dimensional object, okay, this is its cross section. The simplest way to actually get data is to get a huge source, X-ray source, or a line X-ray source, okay, so that is generating parallel rays. This is again conceptual, in practice is never done this way, but in conceptually this is the easiest way. You have a huge source like a huge LED source or something, and you just take a shot, you will get an image, some image, then you rotate either this about an axis like you do in a CT scan, or you rotate the detector and source pair about this axis, the object's central axis, and then you get a sequence of images. If this is your let me draw some coordinates here, we will call this the xy plane. No, let's do this. I think I used z the last time. I will change the notation now. So I am going to call this ray direction is one axis, and then this is the other axis, this is the other axis. Okay. So far I have used xy for the plane, earlier I had used z for this, for the ray direction. Let us just stick to that for a second and see where we go with it. This will be x and this will be y, one of them is x, the other is y, does not matter. If you have this coordinate system and you have this 3-dimensional object, then how you will generate a sinogram is the following. So for a given value of y, according to this coordinate system, this is some given value of y, you take the intensity data, this will be like your p theta of t, and then for the same value of y you stack these values of p theta of t for different theta, and you will get the sinogram. And then you do your usual Fourier slice business like we discussed, and then you will get not f of x y, but in this coordinate system you will get f of x z in this case. Okay, that is for one slice. So our actual cross section, all that stuff we have been talking about is for a cross section, that is this. So this is the same as this, and this is in the x z plane. Okay. Now if you have a big source like this, you can do the same thing for a different y slice, and you can get values over here, you can get a different y slice over here. So you can get different slices, you corresponding x z you will calculate. So now you will have a sequence of stacks in the y direction, all reconstructed using the same scheme, and you stack them up together and you will get the full 3D field. Okay, and that is typically how well, it is not typically how it is done, but conceptually that is how it is done. Okay. Typically what will happen in a practical situation is you will not have a big tube-light type of source making X-rays, because that almost certainly never happens. You will have a point source, and if you have a point source it will not generate parallel rays, it will generate a cone beam, what is called a cone beam, right. And when you have a cone beam you will start seeing parallax essentially, because some beams will go slightly larger distance compared to others. So when you rotate you will not get parallel information, but you will get information depending on the angle with respect to the source position. Those are things you have to account for, we will talk about them at the end. There is something called the Feldkamp algorithm that handles cone beam projections. But basically the idea is you do some geometry there, transform it to a form that looks like this. Once you bring it to a form that looks like this, you can basically do the usual Fourier slice stuff and recover the cross section data. Okay. So that is basically how you reconstruct from projections, from individual projections using the 2D Fourier transform, and then invert the 2D Fourier transform to get the actual cross sectional data. So in the next session I will probably bring some data to show you actual experimental data and what it looks like and what the corresponding sinograms look like and how you can actually use that for looking at internal structures of objects.